discovered copper oxidizable by 6 molar nitric acid solution, but not oxidizable by 9 molar sulfuric acid solution, from which we reached the sound conclusion that in that system, nitrate ion must be responsible for oxidizing copper. But the 6 molar hydronium ion, the 9 molar hydronium ion, which is what we have in 9 molar sulfuric acid solution, can't oxidize copper, then we're not going to expect 6 molar hydronium ion to do the job. Given that in the 6 molar nitric, we have 6 molar hydronium ion. Furthermore, even though we didn't do this investigation, if we try copper in 1 molar nitric, we'll get no reaction. So, from this we can decide that it must be concentrated nitrate ion which is doing the oxidation of copper, or concentrated nitrate ion supported by concentrated hydronium ion. Why is that a possibility? When we developed a half reaction involving nitrate ion converting to NO, which I rewrote here, we find that hydronium ion is a participant in the chemistry of this half reaction. Right? So, what I have done was to again place a piece of copper, a strip of copper, in the 9 molar sulfuric, because that's got the concentrated hydronium ion. And here I've got a strip of copper in 6 molar sodium nitrate. Nothing going on in either one. So, let's take, this has been standing for 10 minutes at least, let's take some of the 6 molar sodium nitrate, where nitrate ion is present in high concentration, and add it to the 9 molar sulfuric. Because, in essence, we now have in this system an inventory which is that like concentrated nitrate. So we should know the reaction is going to occur. Actually, by trying the copper strip in the 6 molar sodium nitrate and getting no reaction, we're already in position to decide that beside concentrated nitrate ion, we also need concentrated hydronium ion to get copper to be oxidizable in this system. And already, after having added some of the concentrated nitrate ion to the sulfuric acid solution 9 molar, we're developing our color characteristic of the production of copper. If I leave this in here for any length of time, it will become more and more blue, more and more intense, and as we did previously. See the bubbles coming off the copper surface? Why, of course. I'll stop this because, again, although NO is not particularly dangerous, nitric oxide, NO2 is, which is what we'll get when the NO arises from the system and mixes with that atmospheric oxygen. Now we'll proceed with additional examples of how to develop equations for half reactions, after which we can couple a half reaction, if we so desire, to get a net redox reaction, a pursuit in which you engage during Tuesday discussion class. But as usual, the various discussion classes have many different degrees of progress, and I want to be sure everybody gets the same overall treatment. So, we'll start at the top, question 2215, which was silver being oxidized in 6 molar nitric acid solution. The chemistry is essentially the same as that as copper being oxidized in 6 molar nitric acid solution. Silver converts to silver ion AQ, and here is the half reaction which shows the reduction of nitrate ion supported by hydronium ion to make NO as the reduction product along the water molecules. Part 2 of question 15 says, if we perform the oxidation of silver in aqua regia, why would we find this oxidation more favorable than this oxidation where silver is in nitric acid solution? Now this obligates you to know what the heck is aqua regia. Did you read about aqua regia in the notes? This name, aqua regia, kind of sounds like it has something to do with royalty. Aqua regia, the water of royalty. Why so? Because this unusual water has the capacity to readily oxidize very unreactive metals, metals which are prized by royalty. What kind of metals are we talking about? Gold, silver, platinum, valuable, expensive metals. So, how does aqua regia inventory? What is aqua regia? If you read about it, you know, or should know. The solution prepared by mixing concentrated hydrochloric acid solution with concentrated nitric acid solution. So, principal system inventory, besides water molecules, hydronium ions at high concentration, nitrate ions at high concentration, so far just like concentrated nitric acid solution, but also chloride ions. Now, chloride ion has the habit of being able to react as a Lewis base with a number of oxidized transition metals. That's why chloride ion, the added ingredient to nitric acid solution to turn it into aqua regia, is necessary. Well, specifically, why is the oxidation of silver more favorable than aqua regia? Is silver chloride more stable than this stuff? Yes. Got the half reaction table? Table 2, look at it. You're looking for the half reaction in which silver is oxidized to silver ion. That shows an E0 value of minus 0.80 volts. Not a very favorable process. But above that in the table, you'll see the oxidation of silver in the presence of chloride ion. That makes silver chloride. E0 value is minus 0.22 volts. Again, minus, but a whole lot less minus than the oxidation of silver to silver ion. Because silver chloride is a heck of a lot more stable thermodynamically than this stuff. That's why this oxidation process is much more favorable than this oxidation process. Part 3. It is true that if we take concentrated nitric acid solution and use it to oxidize metals, which are much more powerful reducers than metals like silver and copper, like zinc, we can reduce nitrate ion to a much lower oxidation state of nitrogen than NO. When we do this reduction with zinc, we get nitrogen gas. If we do this reduction with magnesium, we'll reduce nitrate ion all the way to ammonium ion. In nitrate ion, as we've already recognized, the oxidation state of nitrogen is +5. What's the oxidation state of nitrogen in ammonium ion? What is it? In ammonium ion, what is the oxidation state of nitrogen? -3. Took it all the way from +5 to -3. A huge change in oxidation state. And because of nitrogen's position in the periodic table, family-wise, you can recognize that the lowest oxidation state achievable by nitrogen is -3. as it is in ammonia or ammonium. Any difficulties in developing this half reaction when zinc is the reducer and nitrate ion is reduced to nitrogen? I've written the components of this right here. That's what we know so far. Nitrate ion, as zinc is oxidized to this, nitrate ion is reduced to this. What would you do to proceed in developing this half reaction equation? You think you might have to do this on Lucy next week? Why do we even ask? Well, I suggest the first thing you do is this. That seem reasonable? I've got to murder 2 nitrogen atoms if I want to make a nitrogen molecule. Okay? Now then, should I again write the nitrate ion Lewis structure? I'm not going to do it. You already did it. We did it last time. In this case, how many -2 oxidation state oxygens do we have to strip in total to make our nitrogen molecule? How many in total? 6. Because we got to clobber 2 nitrate ions to make our nitrogen molecule. And what clobbers these -2 oxidation state oxygens as they are put into solution by breaking the NO bonds heterolytically to produce oxide ions? What clobbers these oxide ions as they are put into this system? What will clobber oxide ion in any chemical system? The strongest acid present in high concentration. And in this system, what is that acid? We're doing this in nitric acid solution, 6 molar. Hydronium ion. So if I want to clobber 6 oxide ions, how many hydronium ions do I need in this acidic solution? I heard a vote for 6, I heard a vote for 12. The 6 vote became a 12 vote. Magically, the judges have changed their decision. Shall we stick with 12, or has anybody else got a different vote? We wrote the reaction equation last time for hydronium ion with oxide ion. So in addition to making the nitrogen molecule, what else are we making? What? Water. How many waters? How many waters? If I'm clobbering 6 oxide ions with protons in acid solution, each of the 6 oxide ions converts to a water molecule. And I need 12 hydronium ions to do this. And each one of the hydronium ions loses H+. So how many more waters am I making? So how many waters am I making total? You do have to do some counting. What's the magic number? If you don't see this, think about it. It's not difficult. 6 oxide ions are converted to water, and 12 hydronium ions are deprotonated to do this. That makes 12 more waters. That's 18 total. So what's my electron multiplier? Yeah! How many? 10. Does that keep with total change in oxidation number? Each nitrogen is +5. Each nitrogen is 0. But how many +5 nitrogens did I murder? 2 of them. So I took 10 plus and turned it into 0. That means an electron. That's it. Part 4. Chemistry which you will observe if you place piece of aluminum in concentrated sodium hydroxide solution. Hydrogen will be liberated as the aluminum goes into solution. The aluminum will go into solution as the so-called aluminate ion. Have you any familiarity with the aluminate ion? Here's the aluminate ion. What's the familiarity you have established with aluminate ion? You do some chemistry with it this term if you're in laboratory? Assignment 4? What do you think the structure is of the aluminate ion? Structure. Octahedral. See this picture I drew here? If I took away chromium-3 and put in aluminum, I'd have a picture of this. And how can I? Very simply, write this half reaction equation, where I know aluminum is what's being oxidized, and I know this is the aluminum-containing oxidation product. All I got to do is remember my inventory for the system. I got water and hydroxide ion all over the place. So to make one of these, I need 2 water molecules and 4 hydroxide ions. So I put them in. Done. The other part of the puzzle is deciding what's the hydrogen source. Well, in the system, I've got water and hydroxide ion as my potential sources of hydrogen. Why do I have every reason to conclude fairly that water will be my hydrogen source, not hydroxide ion? In doing the redox demonstration, did we not find that the production of hydrogen by redox is pH dependent? Did we not find, for example, that zinc in pH 7 water does nothing, but zinc in pH 0 water goes like a charm? Didn't we find that out? Which means what we found out is that water does not do any effective job of oxidizing zinc, but hydronium ion does. Because the difference between water at pH 7 and water at pH 0 is principally what? What's the difference? Main difference. Water pH 7, water pH 0. Hydronium ion concentration. 10 to minus 7 versus 1 molar. So, I'm concluding from this that my stronger hydrogen-containing acid is going to be my best oxidizer if hydrogen is a reduction product. Well, what's the better acid, water or hydroxide ion? Enough said. Part 5. If I oxidize aluminum in the 6 molar sodium hydroxide, how don't I get this stuff? Come on now. This is an acid. I'm not making this in hydroxide ion. Right? I should have wrote. Not in present zone. Part 6. In laboratory this term. How many of you expect to do assignment 10? As the syllabus tells you. Any points you earn during assignment 10, and perhaps the unknown analysis for assignment 11, whatever score you get, add it to your total points. And as the syllabus also says for 46 laboratory, once you've accumulated 900 or more points, what grade have you made? A. But yet I will have students, I'm sure, likely not from this class, but I'll have 46 lab students coming to me and say, do I have to take the final? And my answer to that question is always yes. And they'll say, but I have over 900 points. And I'll say, so? So why do I have to take the final? It's because you asked me the question. And I'm telling you, the final exam is a good learning experience. Then they'll ask the critical question. If I take the final and get a 0, will that affect my grade? I said, no, you don't even need an A. It's interesting when students can do it. Like me, I'm going to tell them to take the final because it's a good learning experience. And then they'll walk away saying, you dirty son. One of the experiments you'll do in assignment 6, 10, pardon me, in lab, is to find out that chromite ion, that's a short abbreviation name for this stuff, which contains chromium in the +3 oxidation state, can be oxidized by hydrogen peroxide to chromium. And as question, part 6 of question 2215 in the notes tells you, the reduction product is hydroxide ion. Well, if hydrogen peroxide is the oxidizer, and hydroxide ion is a reduction product, then I can write this. Now, for reasons which I just don't understand, I've had quite a number of students in the past who look at this statement as it stands, and they seem not to be able to turn this into an equation. And I don't understand. So I'll ask you, let's see if you have trouble with this. What do I do to turn this into an equation with respect to material balance? Material balance. That was really hard, wasn't it? Really hard. All done. Electrons? Done. Now, chromite ion becoming chromate ion. Remember, this reaction system, pardon me, contains hydrogen peroxide, but it contains hydrogen peroxide in a strongly basic solution of sodium hydroxide. I think it's 3 molar, what we use in lab. I don't remember what it said. Okay. And this statement, as it stands, shows me that I'm converting 6-coordinate chromium. That means chromium is a Lewis acid. It's connected to 6 Lewis bases, 4 hydroxide ions and 2 water molecules. Here's a pictorial illustration of this species. Octahedral, like this. And this statement, as it stands, also tells me that I've got to make oxide ions someplace along the line. Because in this, the chromate ion, I've got 4 oxide ions which are coordinated, bonded to chromium. Well, how am I making these oxide ions? Well, in the system I've got water, and hydroxide ion. These are my oxide ion sources, not hydrogen peroxide. Keep in mind how we play this analysis game for developing redox reaction equation. We separate reduction from oxidation. This is the half reaction corresponding to oxidation. This is the half reaction corresponding to reduction. So I've got to get these oxide ions from either water molecules or hydroxide ion. Which? From which of these am I getting my -2 oxidation state oxygen known as oxide ion? This one? Why? Oh, we got to break 1 OH bond to do that. Here we got to break 2 OH bonds to do that. You think, since I'm breaking the same kind of bond, it's got to cost me twice as much energy to do this as it does this? Well, which one am I going to do then? The energy cheaper process. Now then, let's go back and look at this picture. Do you think I'm going to, in turning this thing into this thing, you think what's going to happen is a hydroxide line that's in solution, because I'm doing this in sodium hydroxide solution along with the hydrogen peroxide. Do you think the hydroxide line in solution is going to experience this phenomenon? Or do you think it's a good bet that the hydroxide ions in this system, which experience this bond-breaking phenomenon and become converted to oxide ions, will be these? Because they're already connected to chromium. Doesn't that seem more reasonable? These are already connected to chromium. So let's tear these guys up and have these guys leave the first coordination sphere. Have these guys engage in bond-breaking process with chromium. And there I have it. I got my chromate ion. So, if nothing else, I hope that this structural, that this analysis, the analysis of the system was supported by this structural analysis. In any case, as I tear up my 4 coordinated hydroxide ions, these 4 Lewis-based hydroxide ions, and turn them into oxide. What else is going into the system? As I wreck these hydroxide ions to make oxide ions, what else am I putting into the system? What else am I putting into the system? H plus. Isn't that interesting? This chemistry is giving hydroxide ion, coordinated hydroxide ion, to behave in what fashion? Let's do this. This coordination chemistry is marvelous stuff. This is the peak in coordination chemistry. That's the main topic of chapter 24. How much of chapter 24 I don't know. I don't know how much that we'll be able to discuss. We'll discuss some coordination chemistry. Marvelous stuff. You think chlorophyll is important stuff? You think hemoglobin is important stuff? It's all coordination chemistry wrapped up with the very important behaviors of those 2 molecules. All right? In this system, as I convert these coordinated hydroxide ions to oxide ions, what eats these H pluses? What eats H plus whenever H plus is put into a chemical system? Have you recognized that H plus is the very heart and soul of Brown's acid-base chemistry? Have you recognized there cannot possibly be a stronger reaction than simple H plus? It's there. It's H plus. That's what Brown's acid-base chemistry is all about. What's going to eat H plus if H plus is put into a chemical system? What's the answer that's always right? The strongest acid present in the pot, present at high concentration. Pardon me, strongest base, let's say this right. The strongest base present in the pot at high concentration. Well, in this system, what is that base? Hydroxide ion. How many hydroxide ions do I need? 4. So beside chromate ion as a product, what else? How many? How many? Don't forget these 2. And now we have material balance. To turn this into an equation then, we need an electron multiplier. What is it? That gave with oxidation number change. In this chromium is +3. In this chromium is +6. You betcha. Now we'll ask one more question. If I'm going to take this half reaction and couple it with this half reaction, which is what I have to do if I want the net redox reaction, I can ask the question, As this system runs, does pH stay the same, increase, or decrease? As this system runs, does pH stay the same, increase, or decrease? One of these has got to be correct. Well, let's have a vote. pH increases. pH stays the same. pH decreases. Yay! Because to put these together, I have to multiply this one by 3 and this one by 2, which means I will, by this half reaction, manufacture 6 moles of hydroxide ion, while at the same time in this system, I'll be chewing up 8 moles of hydroxide ion. So this system involves a net consumption of hydroxide ion, which means the pH is coming down. 7, easy. Another part of question 2250, which students often stumble on, and I don't know why. So I'm directing your attention for part 7 to look at table 2. Specifically, table 2, half reactions 37 and 38, if my notes are correct. Because if you examine the information that's in the notes regarding part 7 of question 2215, you should realize that silver ion is being reduced to silver. Okay, so what? While iron in the +2 oxidation state is being oxidized to iron in the +3 oxidation state. Do you see this? Following from the statement of the question. We'll then look at the half reactions, which I told you to examine. 37 and 38. Because all that's happening is hydrated iron +2 is converted to hydrated iron +3, as Ag plus Aq is converted to silver. So we'll ask you this one more question. What's E0 for this process? E0 0.03 volts. Because in this coupling process, I will reverse the silver-silver ion reaction, which will change the sign of the potential to plus 0.80 volts. The iron 2 to iron 3 reaction is operating at a potential of minus 0.77 volts. So the system is running at a plus 0.03 volts. Understand the state condition. But the voltage is positive. So it's a spontaneous reaction. Part 8. Electrochemists commonly refer to part 8 as an illustration of Otto redox. I haven't chosen to make any particular point of Otto redox phenomenon, but all this fancy sounding term Otto redox means is that for the redox system in question, the stuff which is being oxidized is also the stuff which is being reduced. That's what Otto redox means. The oxidizer and the reducer are one and the same. In this case, cuprous oxide, copper in the +1 oxidation state, is converting to hydrated copper ion, which means copper +1 is becoming copper +2, oxidation state change Y. While in the same system, cuprous oxide is converting to copper metal. I've done this before as a demonstration because we've got some cuprous oxide in the back. All you need is some sulfuric acid solution. I think 2 molar is what this is going on. But it's a messy looking system. It's hard to see the copper metal which is being produced. If I did this demonstration and everybody crowded around the beaker, you'd see what's going on. But if I just do it here, you won't see much. What are we going to do to turn these things into half equations? Well, let's start with this. This will establish material balance for copper in both the oxidation half and the reduction half. I'm running this, if my memory is right, 2 molar sulfuric. Is that what the notes say? 1 molar sulfuric. Well, there's my principal system inventory. And the sulfuric acid solution. To make 2 moles of this, I need 12 moles of water. Well, I'm running this in a water-rich system, so let's put it in the water. So the only other puzzle part is, what the hell happened to this oxide ion? What do you think happened to it? I heard a vote for oxygen gas. Anybody going to support that vote? If it was oxygen gas, would oxygen gas not also be an oxidation product? Have we indicated that oxygen gas is an oxidation product? No. So what this amounts to is putting oxide ion into a solution which is strongly acidic. Would you accept that? 1 molar sulfuric acid. So what the hell is going to eat these oxide ions? Hydronium ion. That's the best acid in the bottle. How many hydronium ions? If I put oxide ion together with 1 hydronium ion, I'm making hydroxide ion. I'm not making any hydroxide ion in the acidic solution. So we'll accept your second one. And when 2 hydronium ions murder the 1 oxide ion, what do we make? What do we make? 3 moles of water. So, do I really need 12 moles of water here? How many moles of water do I really need? None. All right? Now, here again, oxide ion is going away. Well, we know how to deal with that. Material balance established. Put it in the electron multiplier, add it up, done. Now, parts 10, 11, and 12 of question 2215, we've already dealt with. If you don't recognize why, please ask. We've already dealt with these. So let's jump to part 13. And take a look at the redox chemistry that takes place in a system which I expect all of you to possess. Automobile storage battery. Technically, the automobile storage battery is very simple. Made from lead dioxide, which at a glance I hope you will recognize contains lead in what oxidation state? +4. And 4.5 molar sulfuric acid solution. Well, we know enough about sulfuric acid solution at fairly high concentration so that we can immediately write sulfuric acid solution inventory. Principal components: hydronium ion, hydrosulfate ion. That's it. Chemical composition of the lead storage battery. Now, we'll provide a note. At each electrode, lead sulfate is produced. What do you think your automobile generator does? What is the function of your automobile generator? Recharges the battery. Now, how does this process take place chemically? So, chemically, what does your automobile generator do? As you motor down the road, what does the generator do chemically? If I'm making lead sulfate at each electrode, and the starting materials for the battery are lead and lead dioxide respectively, what does your generator do chemically? It returns lead sulfate to lead at which electrodes? Anode or cathode? In the car battery, is lead an anode or cathode component? In the car battery, is lead dioxide an anode or cathode component? What takes place at the anode? Oxidation or reduction? Oxidation. And at the cathode, reduction takes place. So at the anode, in your lead storage battery, you will find what? Lead or lead dioxide? Lead. So what your generator does is to turn lead sulfate back into lead at the anode and lead sulfate back into lead dioxide at the cathode. So, for anode, we can start with this. For cathode, we can start with this. In this system, what is the sulfate ion source? Hydrogen sulfate. I haven't seen one damn general chemistry textbook yet get that right. And people wonder why I want to use these dumb books. So with what we have on the board, I charge you with the responsibility of continue operating on these skeletons so that on Monday you can write the correct half reactions for the lead storage battery. And if at Monday start of class you're not capable of doing that, 3 million points off. There.